Today we are going to learn about mastering Python multiprocessing with pool. Discover how to efficiently manage multiple processes using Python's pool class, crucial for optimizing performance in applications requiring parallel processing.
Welcome to our video on mastering Python multiprocessing with pool. In this session, we'll explore the pool class from Python's multiprocessing module, a powerful tool for managing multiple processes. This class simplifies the process of parallelizing your code, allowing you to execute multiple tasks at once, which is crucial for optimizing the performance of applications with significant processing demands. By the end of this video, you'll gain a comprehensive understanding of how to implement and manage a pool of worker processes to execute tasks concurrently, setting you on a path to writing more efficient and effective code. To begin utilizing the pool class, we need to know how to set it up. First, you'll typically import the pool class from Python's multiprocessing module. You can create a pool object by specifying the number of processes you wish to run concurrently. For instance, pool processes equals 4 initializes a pool of 4 worker processes. This setup allows for parallel execution of tasks, effectively distributing computational workload across these processes. A common mistake is setting too many processes, which can lead to resource exhaustion, so it's crucial to balance the number of processes with the available system resources. A practical demonstration of this setup can include a simple task, such as computing squares of numbers concurrently. This example will highlight how tasks are split across processes and executed simultaneously. Understanding this basic setup is foundational for more advanced pool functionalities. The pool class provides 2 primary methods for executing tasks: apply and apply_async. The apply method is used for synchronous execution, meaning it waits for the task to complete before returning a result. This method is straightforward and ensures tasks are completed in a predictable order, but it may not fully utilize the available processing power. On the other hand, apply_async is designed for asynchronous execution. It dispatches tasks to the pool and returns immediately, allowing you to handle other operations while tasks complete in the background. This method is ideal for maximizing concurrency and is often used when the order of task completion is not critical. Through code examples, we'll demonstrate how each method works, highlighting the differences in execution flow and performance. Understanding these methods is key to selecting the right tool for your specific use case.
When using apply_async, managing asynchronous results becomes a crucial task. The method returns an async result object, which can be used to retrieve the result of the task once it's complete. This object provides several methods, such as get for fetching the result and ready to check if the task is finished. Implementing callback functions is a powerful way to handle task completion. You can specify a function to be called with the result once the task completes, allowing you to process data or trigger further actions seamlessly. This approach ensures that your application remains responsive and efficient, even when handling complex or time-consuming tasks. We'll look at examples demonstrating how to implement these techniques, ensuring you can manage your asynchronous tasks effectively while maintaining data integrity. Efficient resource management is crucial when working with multiple processes. The number of processes you allocate should be balanced with your system's available resources to avoid overloading. A common strategy is to set the number of processes to the number of available CPU cores, allowing each core to handle a process efficiently. However, some tasks may demand more resources, requiring dynamic allocation strategies that can adapt to current system loads. Monitoring system performance metrics, such as CPU and memory usage, can provide insights into how well your application is utilizing resources. Tools like Python's pseudo library can be invaluable for this purpose, enabling you to make informed decisions about resource allocation. We'll explore techniques and best practices for managing these resources effectively, ensuring your applications run smoothly without unnecessary strain on your system.
In any programming task, error handling is a critical component, and this holds true for multiprocessing with pool. Common errors in pool operations may include resource exhaustion, incorrect task parameters, or unexpected exceptions during task execution. Employing robust error handling strategies is essential to prevent these issues from disrupting your application. Using try-except blocks within task functions allows you to catch and respond to exceptions gracefully. Additionally, Python's built-in logging module can be used to record error details, providing valuable insights for debugging and performance analysis. We'll go through practical examples to demonstrate these techniques, ensuring you're equipped to handle and debug pool operations effectively. Understanding these error handling strategies will enable you to maintain the reliability and stability of your multiprocessing applications. To appreciate the power of Python's pool class, it's helpful to examine real-world applications and performance benchmarks. Multiprocessing is particularly beneficial in scenarios involving compute-heavy tasks, such as data processing, machine learning model training, or large-scale simulations. By parallelizing these tasks, You can achieve significant performance gains, reducing execution time and improving efficiency. Benchmarking techniques can provide a quantitative measure of these improvements, allowing for a comparative analysis with single-threaded execution. We'll discuss various case studies where Pool has been successfully implemented, highlighting the performance benefits achieved. These examples will not only demonstrate the practical applications of multiprocessing but also inspire you to apply these techniques in your projects. Deploying applications that use Python's Pool class in production environments requires adherence to best practices to ensure stability and performance. It's crucial to adapt your multiprocessing strategies to the constraints of your production environment, such as hardware limitations and security policies. Ensuring that your code is robust and secure is paramount, particularly when dealing with sensitive data or executing tasks with elevated privileges. Maintaining code readability is also essential, as it facilitates collaboration and future maintenance. Strategies for scaling your applications, such as load balancing and dynamic resource allocation, will ensure that your application can handle increased demand without compromising performance. We'll explore these best practices in detail, providing you with the knowledge to deploy your multiprocessing applications confidently and effectively in production settings.
For those looking to push the boundaries of what's possible with the Pool class, advanced techniques and customization options are available. Customizing Pool behavior to suit specific needs can involve adjusting configuration options, such as process affinity or task prioritization. Using context managers with Pool can streamline resource management, ensuring that resources are released promptly when no longer needed. Integrating Pool with other libraries, such as concurrent.futures or third-party task schedulers, can further enhance functionality and efficiency. We'll delve into examples of advanced usage scenarios, demonstrating how these techniques can be applied to tackle complex multiprocessing challenges. This exploration will equip you with the advanced skills needed to customize and optimize Pool for your unique requirements, unlocking its full potential in your applications.
Despite careful planning, issues can arise when using the Pool class in multiprocessing applications. Common problems include deadlocks, race conditions, and unexpected process terminations. Identifying these issues early and applying effective troubleshooting strategies is essential to maintain application performance and reliability. We'll explore techniques for diagnosing and resolving these common problems, including using Python's built-in tools and third-party utilities for monitoring and debugging. Understanding the root causes of issues, such as shared resource contention or incorrect task synchronization, will enable you to implement preventive measures and solutions. By mastering these troubleshooting strategies, you'll be well prepared to handle any challenges that arise in your multiprocessing projects, ensuring smooth and efficient execution.
As we conclude our exploration of Python's Pool class in the multiprocessing module, let's recap the key concepts covered. We've delved into setting up a basic pool, using apply and apply_async, handling asynchronous results, managing resources, and best practices for production environments. Mastering these techniques is crucial for optimizing performance in applications requiring parallel processing. I encourage you to practice these concepts in your projects and explore the wealth of resources available for further learning. As you continue your journey in mastering Python multiprocessing, consider diving into advanced topics and techniques, expanding your skill set, and enhancing your ability to tackle complex computational challenges with confidence.